Well, it looks like we're just about there. Welcome back, folks, so far. And it's official. This is now our last class. Welcome to making it to this point so far. Kind of a light class, but it is close week. This is exam prep week. People are usually kind of tired getting through this week, and that's why it's a good idea to just mainly focus on reviewing problems rather than delving further and further into the course. But for a quick wrap up of announcements, we are on exercise 11 of this sample final exam problem list here. We should be able to finish this document today's class, but anything that gets left over, I will come back to and get them totally solved before we're going into the weekend. Other announcements are, well, that these extra credit opportunities have been sitting here for quite a while. This one on the bottom is new, unfortunately, should have been posted quite a while ago, but they do have some expiration dates on the first one. First one is any late work that you may have missed submitting earlier in the semester, I will accept for full credit, even if it's part of assignment you didn't get to. Especially take a look into anything that was marked with the blue pen. Those are usually problems where maybe you missed a problem or forgot an element of a problem, like a part B, for example. You're always welcome to start turning that work. The other one is the course evaluation, and the math department has to close this one on Friday. I don't know the specific time, but it's usually in the evening. So this is not one you definitely want to wait on since it can evaporate on us at the end of Friday. But this is where we're at so far. We're going to finish out week 15. This will be our last time meeting for a class like this. And then we'll meet again, potentially, if you're meeting in the classroom for the final exam. That's for the in-person folks. And even if you're in the online section, if you prefer to just come into the exam room, maybe email me so I have enough exams and are prepared for you, but you're welcome to come in room CHE 215 for that exam. I'm also giving an earlier exam, 5:30 to 7:30 p.m. for folks who just don't feel like 8 to 10 p.m. is their best time to take an exam. For the online section, oops, sorry, I've got a little feedback. For the online section, I've sent over the exam to various testing centers, the Pocatello Testing Center and the Idaho Falls Testing Center. If you haven't gotten an email from me to say you're welcome to use a link or call a number to schedule an exam, please let me know right away and I'll get that fixed as soon as possible. So that's where we're at so far, folks. Any questions at the moment before we get started? Or maybe a better question, any problems that folks would like to discuss before we go back to this document here? Okay, let's give these problems a try. We're now on exercise 11. And as far as the real exam goes, maybe just a little bit more information about it. I'm not really in the habit of writing a brutal final exam for any one of my classes. In fact, when I write down this information right here, the grade on the final exam is higher than the minimum grade among exams 1, 2, and 3. What I'm specifically mentioning here is the curved final exam grade. I never curve exam 1, 2, and 3, but I always curve the final exam because the goal of this exam is not to cut down people's grade in the class. The way I actually curve it is I look at the course average for everybody going into the exam. If that average moves down, say by about 5% or more, it tells me how much I need to curve this exam to bring it back to a balance of 0. My goal is really not to change your grade at all on this exam, and so I curve it with that knowledge. And again, it's going to be the curved final exam grade that may to replace your minimum grade amongst exams 1, 2, and 3 for that extra credit opportunity there. Other reasons why the final exam is sometimes curved is a lot of people have done really, really well on these exams. And that's typical with every class I teach. Sometimes I put a couple questions that have just a slightly harder element inside of it, just to see how far people can go with those kinds of elements. We'll look into a problem just like that on the review there. But it's not a totally fair question unless it's also curved. So Most of these problems are going to be highly routine. There might be a couple extra challenging kind of problems, but not meant to drop your grade, just to see how people attack a problem like that, those kinds. So with that all said, let's jump back into problem 11. There's going to be problems where we have to do some proofs, not a whole bunch of proofs on the exam. Expect one where it's a chapter 4 proof technique, and expect another proof where it's going to be something by induction, either regular induction like this one, or strong induction like this one. Several edits on this problem. Sorry if you're keeping track of all those edits. So I'm not going to ask 2 induction problems. I feel like that's double jeopardy. It's pretty much going to be one or the other. So let's start at the beginning of these proofs. This one is asking us to do a proof by contrapositive of a statement, something we've probably proven before, but really for the sake of review, this is more about the method, less about the mathematical content down here. So when it says proof by contrapositive, that means we'll prove the statement that says the contradiction or the negation is a better thing to say of this statement. The negation of n is even is n is odd. I'll just use the right arrow to say implies. Negation of this statement would be n squared is odd. So this is the statement we would rather prove. And it's a good idea. This is an easier statement to prove. And here's how the technique starts. Well, it started right here. Here's how the proof begins at this point. So for the proof, we begin at this statement with the goal of getting down to this one in our ultimate conclusion. So let's just start off by saying this part. Assume n is odd from the beginning. Then we want to immediately say, what is the meaning of having odd? What does this say right away? We'll say, quantifying a statement. This means there exists an integer k such that n is twice k plus 1. Already very similar to the proof that we looked above on problem 10. Once we have this statement down, we can now work on the n squared statement. Let's say here, then n squared by substitution is 2k plus 1 squared. Bit of algebra gives us 4k squared plus 4k plus 1. A little bit more algebra because we're going for the form of odd means we want to have a 2 factored out and then a plus 1. So we only look to the first 2 terms here since we already have our plus 1 lined up. Factor out a 2, leaving behind 2k squared plus 2k plus 1. This is not quite yet the end of the proof. We have to make a conclusion, but we also have to justify it at the same time. This is not guaranteed to be an odd number. The only way it's odd is if the thing in the middle is actually an integer. Oh, this is not a well quantified statement. Let's see if we can fix that. Full disclosure, I'm working on a little bit of insomnia, so if you see anything weird on here, let me know. We'll get it fixed right away. There exists k in z is a better way to say that. We have to have a set here to really quantify that. So we need to justify that that's in the set k, but everything here is just multiplications, additions. Using the closure property of integers, we can conclude the following. Since 2k squared plus 2k, if we start with integer k, then all these operations here return another integer. We'll just say briefly, is an element of z again, so it's an integer. It follows that n squared is odd. We used a lot more words when we did a proof like this one in the prior section, but that's just because we were starting to learn this kind of proof technique. If you're a little bit terse, but you have all the right elements inside of your statements, it might be just as short as a proof as this one. Maybe you might be able to optimize a couple statements here and make it even a little shorter. But any last questions, folks, running through problem 11?
Professor, for those
Yeah.
questions, you don't need us to say that the original one is therefore true. We can just end it on that last note there, and that's okay?
Yeah, that'd be absolutely
Perfect.
fine.
Okay, thank you.
Yeah, we added a lot of extra details last time, but it's because we were really saying what was the contrapositive, how did it logically connect to the original implication, but we've done a lot of that kind of work. And so you're absolutely right. If you end it right here, I'll assume those were the thoughts you were having all along, and that's a qualifies as a perfect proof at that point.
Thank you.
Yep, absolutely. Other questions so far? Okay, let's try out the other ones. So this one was write down a contrapositive, then do a direct proof of the contrapositive. And that was a lot of what our methods were in chapter 4. This is the kind of stuff you'll see on the real final exam. It gets a little bit hazy once you get into induction. Well, it's just like before. We took a lot of time doing induction when we were in chapter 5. That's because we were just trying to break down what is the statement really trying to say? How does the proof method really work? Now that we've done all that hard groundwork of learning what induction is, this proof might go a little bit faster as well. But it's a trickier problem, so let's actually take a little bit more time with this one just to be sure we have everything lined up. And we know what our real goal is. Sometimes that's the big confusion of induction. What are we even trying to do in the very first place? So here's a tie-in to chapter 3 on quantifiers. We want to bring in a predicate function p. Let me start by saying then, let Pn be defined by the statement Pn is that the summation I goes from 1 to n in summation of I. So the first n integers added together can be re-expressed as the last integer n plus the last integer increased by 1 multiplied divided by 2, giving us a nice summation formula. The function that we just defined, being a predicate function, p, its truth is going to depend on n. And that means our goal here is to show it's true for all n to really prove this statement up here. But because it's a predicate function, you can also say p maps from, let's see, prove the following statement. They didn't say for what values this qualifies for, but let's just say this is going to be z greater than or equal to 1. So we'll start at 1 on this one. It maps to the set of Boolean values, true and false. And so we call this predicate function p sometimes a Boolean valued function all at once. So we're really reviewing 3 things in this one problem. A predicate function whose truth depends on some other variable, the fact that it's Boolean valued, and at the same time, proving something through induction. The thing we're trying to prove is, for all n in z greater than or equal to 1, p of n. This is the really, really brave way to say it, but when we started doing induction, particularly in section 5.3, I felt like a little bit more emphasis is helpful, just to remind us this is what the function really is. So we'll say here, just to be really explicit of what we want, Pn maps to true for every integer in that set. So if you started on this line, that'd be just fine as well, but this is us just putting extra information on the notes, breaking down the problem a little bit further as we run through it. Since we're trying to prove something for all n, induction says we need a base case. The base case is going to be right at the first integer. So let's say let n be 1. So we're taking the minimum domain element right here, and we're just going to work our way up until we've mapped to hopefully true every element from the domain z greater than or equal to 1. When n is 1, we're trying to get something mapped to true. We just go over here, look at the left-hand side and the right-hand side, and see what becomes of it. So let's say, then, n becomes 1 in this position. Summation I goes from 1 to 1 is just silly notation now, but that's how that left-hand side would be expressed at that integer. This is just a value 1. Next, we plug 1 into the right-hand side, and we get 1 times 1 plus 1 divided by 2, which is equal to 1 as well. That tells us the equality here is correct, And then it tells us the second thing, this function p of n, when we input 1, gives us this result. This shows p at 1 is true. So that's our base case defined. Let me see if I can squeeze that in there just for extra structure. This is the base case. Well, any questions, folks? Getting through this first phase? Okay, these are graded kind of gently because they are tricky proofs on the exam. And if you haven't picked up yours, I am going to scan it starting on Friday and get it back to you to help with your review. But I usually say it's going to be as a 10-point problem, half the points for correctly writing out the base case or base cases in strong induction, and the other half of the points for getting through the inductive portion. So let's call this next the inductive case. In the inductive case, we're going to increment the integer just by 1. We'll say let n be greater than or equal to 2. Well, we increment it, and then we allow it to be any value larger than that. Then we make a big assumption. This is the inductive hypothesis. We'll say and assume p at n minus 1 is true. And this is well grounded in the sense that if n is 2, this becomes p of 1, and we did show that is true. Our job is to show that this is going to now next apply directly. P of n itself is true. Once we get there, the whole proof is complete. So just to add a little bit more structure, this is an optional line, but sometimes saying where you need to go really helps the brain organize these thoughts. We must now show p of n is true. If we can show that p of n minus 1 true implies the very next value, p of n is true, then the base case can be fed into this argument to show p of 2 is true, then fed back into this argument to show p of 3 is true, and so on until everything up in this set from the domain maps back to true. So that's our goal. And this is the big step that was missed on the exam problem. So if you write down this step, I assure you it's going to help a lot. It's all about what does that mean exactly? When folks didn't write down that, a lot of times the proof kind of went sideways because it became really kind of vague on what the next algebraic steps should be and how to get to our conclusion. So let's say here, just definitively, p n minus 1 equals true means, come back over here, this whole equation is now true. So let's write this out. Lots of ways you can write it out. I'll write it in this form. Summation I equals 1 to n of I. First, let's expand it just to get some better intuition of what's going on here. The problem's as abstract as it is. Adding summation notation is adding an extra level of abstraction. So we can just re-express this whole thing if it helps as, hang on, before we do that, recall we said Pn minus 1. That means n minus 1 would have gone into that position. Let's fix that mistake right there before we get too far along. A little bit of highlighting can't hurt to tie that together. So we're going to sum all the integers starting at 1 up to n minus 1. So plus 2 plus 3 plus n minus 1. Can't hurt to highlight that as well. It has to be directly equal to n times n minus 1 divided by 2. N plus 1 rather, I think I said minus, divided by 2. So the truth of Pn minus 1 means we have this equation here. Really, this is the big part where we get the formula on the right. Now to get that P of n is true, we're trying to show this original equation holds as well. So let's begin by doing the following. Next, we're going to start just on the left-hand side after fixing this spelling there. Next is summation as I goes from 1 to n of I. This can also be re-expanded as 1 plus 2 plus 3 plus so on up to n minus 1, but that's not the last one. We're going up to n this time, plus n. I can't say equals anything because that's our job, to show it's equal to this. So what we have to work with directly is this inductive hypothesis. But we can do that by just using the good old trick in arithmetic, associate whatever we need to associate. This entire section right here is now just n times n minus 1 plus 2, because it's just this written out as well. So it becomes n times n plus 1 divided by 2 plus n. Now we need a common denominator since we have to make this become one fraction. So let's write this as 2n over 2. At this stage, however, we're nearly there. We can put this under the common denominator too. Expand this set, or this side, n squared plus n. Add the 2n. And hang on. I did make a mistake right here. I'm going to blame this on the insomnia again. Anyone see what the mistake is on this side?
Were you supposed to put n minus 1 in front and then n after that?
Yeah, absolutely. I got the
Okay.
n minus 1 here. After coming back and circling and fixing the typo, we have n minus 1 here. And n minus 1 goes into this position, this position. I noticed right here, the algebra went completely sideways, so that was my indication something is amiss. Thanks for spotting that one. So fixing this step, we're throwing in n minus 1 to the formula. It goes here just as you said, n minus 1. It goes here just to n exactly as you said as well. Divide by 2. Deserve some highlighting there. Let's carry that typo down and correct it from this spot. So n minus 1 times n in this position. So it's kind of fun when you have an error that sort of tracks through a whole bunch of steps in algebra. Then finally over here, now let's expand this part. It's n squared minus n. Bringing in this side is plus 2n. So we are obtaining n squared plus n divided by 2. And you know that's the right form once we just factor out n. So this becomes n times n plus 1 divided by 2. And that's what we need to get to. The yellow here is showing all the mistakes that would have prevented us from ever getting to that spot. But now we're there. We connected the formula on the right-hand side with the summation on the left-hand side. And that just means P of n is now being shown to be true. So let's make that conclusion. This shows P of n equals true. And if you end the proof right at that step, I'd say it's totally appropriate as well, because I would assume at this point, you've studied induction a lot, and now you know the inductive hypothesis assumed as true, implying the next integer in the predicate function is true, has really shown it's true for all n. So if you end it right there, that would be appropriate on a final exam. Well, here's the full view of the problem. Wasn't meant to be a tricky one, but induction has a way of sneaking in some tricky elements like we saw right here. Don't forget to make the mistake I did. If you're doing n minus 1, n minus 1 goes here and everywhere else where it could be relevant. Any questions at all, folks, surviving this one? Okay, let's try out the next then. Now it's strong induction, and found that there was quite a lot of typos when I wrote this one in. First typo I had is I just messed up that value there, which caused a problem on this as well. Then I forgot to write in the question. Then I do like to practice these before I try to do them in class. I found out that's not true unless you start at n greater than or equal to 2. So we have to have greater than or equal to 2 here as well. So sorry for all the typos and corrections on this one. But now that we're here, this one is a pretty challenging problem, I have to be pretty honest with. But it's a good one that reviews several concepts all at once. We're going to be dealing with recursion. We're going to be dealing with finding the values of the sequence all at once. and wrapping it together with strong induction. So first, let's just say what we're trying to prove. Starting at integers greater than or equal to 2, despite the fact the sequence starts at 0, 1, and then increments through the recursive formula. If n is greater than or equal to 2, we have an estimate on all the terms of the sequence. They're always less than or equal to 7/4. That's some really interesting information there. So now let's say here, let's define the predicate function, p of n, to be that statement. Nth term of the sequence, less than or equal to this curious estimate, 7/4 power of n. Since this is an induction problem, even though it's a strong induction, we can still say the next type of statement. We're going to prove that for all n in z greater than or equal to 2, p at n maps to true. So let's give this a try. Kind of annoying though when it says it's only going to be true for z greater than or equal to 2. Would have been nice if it was at 0. In fact, it does work at 0, but it doesn't work at 2. So that's why there had to be a revision right here to make this problem more concrete. So our base cases now start like this. We begin at the first minimal value of the domain of the predicate function. So we'll say let n equals 2. Now we have to check this estimate, which means we have to compute A2 on this one. Kind of annoying. It's not listed out here. But we've done that kind of practice before. We'll say here, then A2, through the recursion formula here, it's going to be A1 plus A0. Kind of like the Fibonacci sequence, but just different starting values, slightly different. So A1 is 2, plus A0 is 1. So we have A2 set to 3. Now what we have to check to make P at 2 true is 7/4 to the power 2. 7/4 squared, we're hoping exceeds 3. So let's see how close that gets. At power 2, barely. We have a 3.0625. But that's good. It just had to be greater than or equal to, or better said, maybe the nth term, A2, just had to be less than or equal to this value. It's strictly less than. So this says, since, or let's just jump right to it. We have the estimate is correct. So we'll say here, this shows P2 is true. Since we can observe just by visual inspection, A2 is less than or equal to 7/4 squared. But now we're going to need to do it again, because if we're going to use the inductive hypothesis, and we have a recursion using 2 prior terms, we need strong induction and more assumptions, more base cases as well. So let's say, now let n be 3. We have to compute A3 through this formula. Then A3 is going to be A2 plus A1. You just calculated A2 over here, so let's substitute it in, 3 plus. A1 is provided. So the third term is at size 5, and 7/4 to the power, same power as the integer we set here, cubed. Let's check the value on that one quickly. To power 3, let's say just to a couple decimal places, we get a 5.359. That means it's true. Our term A3 is less than or equal to 7/4 cubed. So we can say next, this shows P at 3 maps to true on our predicate function. So base case is done. Now we're going to do the interesting cases of how does this connect with the inductive hypothesis. It's a little bit more involved. We have to make a string of assumptions, but it's going to start off the same as ordinary induction. We take this last integer right here and say, in the inductive hypothesis, or let's say the inductive case, as our author usually calls this, let n be bigger than or equal to 4. Then we make a string of assumptions. We want P2, P3, P4, P5, up to Pn minus 1, all to be assumed true. We have this in a good foundation because we just proved that base cases here are true in fact. So this statement is not far-fetched. We'll say here, assume P at 2 and P at 3 and down the line until we get to Pn minus 2 and Pn minus 1 is true. So because of the and connectives, we're saying every one of these is going to map to true all at once just by this one equality. So let's take maybe this part right here. Just like the original inductive problem that we took a look into, once we make this assumption, we really want to say what it means because it's going to guide all of our reasoning on the next step. So let's say here, all these things assume true, and we just need 2 of them for an minus 2, an minus 1. Let's start with this one. Since Pn minus 2 is set to Boolean value true, this means, I kind of missed something in my screenshot. We are trying to get that statement. It would mean an minus 2 is going to be less than or equal to 7/4. And avoiding the mistake in the last problem, put n minus 2 on the right-hand side as well. And then we'll do it all over again for Pn minus 1. And since Pn minus 1 maps to true, this means an minus 1 is less than or equal to 7/4 n minus 1. So these are the 2 inequalities we get for free through the inductive hypothesis right here. Let me take a screenshot of this since this is now our target. Try to get to that step. Well, we're about ready to go and show that this is going to hold at n as well. Any questions at all, folks, through this portion of the analysis? Okay, let's make this problem a little bit shorter since we did put in a lot of words on the last one. You might say our goal is to now show that P of n is true, but let's launch right into it. So to show P of n is true, we have to show that that estimate holds. And let's say, now let, or let's say better, now consider an. Our ultimate goal is to show an less than or equals to 7/4 to power of n. First tool we can use is just the definition. An is defined to be the prior term an minus 1 plus the next prior term an minus 2. Well, we're done with that, so there it is, all imported. Now we have to make some connections, but here are the connections. We already have estimates on both of those terms through these 2 steps right here. So let's drop them in right away at this step. This is now automatically less than or equal to 7/4 to the power n minus 1 on the first one, so I'm on that inequality. For an minus 2, we're on this inequality, so 7/4 to power n minus 2 on that one. So we used up the entire inductive hypothesis. Now we're kind of on our own. We have to get here somehow. So we need to manufacture 7/4 here without doing anything illegal in algebra. Somehow, some way, we're going to have to make an estimate. thought on this one. Again, this is possibly why this would be a more challenging exam problem, and there might be one or two questions that are more challenging like this. I'm going to curve the final exam in anticipation of those questions. But the goal is now just to see what can we do with this. This is going to involve some thinking. But one thought here is, if we're kind of stuck algebraically, we always have one great tool, factor something. And we can definitely factor 7/4 to power n minus 2. It's the lower factor, so it's the greatest common factor. So take 7/4 power n minus 2, leaving behind 7/4 here, just to power 1, plus 1 from here upon factoring. And this is getting us somewhere. Our goal is to get to there, right? If we can get 7/4 squared, we'll bump the power up here to power n, and our job is just completely done right at that step. So our goal is to work with that. Here's where we might break off this right here and do some algebra work on the margin. Even if your algebra goes nowhere, I'd say just leave it on your exam paper, unless you can come back to this problem and make some different changes on it. Because I'm really looking into your thinking on this when I'm grading on partial credit. I want to see what kind of things you connect, what kind of steps you might take. And for this problem, here's one way we could go. 7/4 plus 1. Well, it's got to be one fraction. We're trying to get a 7/4 squared to get up to that power. So let's just add this up. This is 7/4 plus 4/4, 4 and 11/4. And recall, if we have 7/4 squared right here, we're all set. We get, well, what is 7/4? That's 49/16. So that tells us, let's get a 16th in the denominator and then just see what else we can try. This is 44/16. So now it's a more complicated fraction. Then again, think about our goal. We want 7/4 squared. That's equal to 49/16. The denominator's settled. Now we could just make an estimate on the numerator, bump it up to 49. Remember, we can't do anything illegal algebraically, but that's fair. That's an estimate. It's an inequality, 49/16. And 49/16 is 7, let me try again, 7/4 power 2. Even better, we're trying to go on a less than direction. So if I plug in something here that's strictly less than, we're still on the right track. So now we have that this is strictly less than 7/4 power n minus 2. It might look concerning, we have strictly less than, but this says less than or equals, a literal Boolean, or not Boolean, but a literal logical connective or there just means one or the other has to be true. Or less than true is going to do the job for us. So now this whole thing becomes 7/4 squared, which means it's now equal to 7/4, add the powers together on this, and now it's power n. And that's exactly what our target was. So once we were there, pretty much we can celebrate at this point. Let's add just a couple flowery words to solidify this. We just showed, if I can zoom out enough, that P of n way up here is true, because an, following all of this logical stuff and equalities, is less than or equal to 7/4 n. So let's declare that the statement right here. This shows P and n maps to true, and the proof is complete. That one deserves an exclamation mark because it is kind of a sketchy proof. Anything that has kind of inequalities going on for it, if you know you're taking elementary analysis, introduction to real analysis, that kind of stuff, lots of this kind of logic gets thrown into the mix. It's a really interesting, creative way to think, sometimes not very straightforward to get to where we need to go. But any last questions at all, folks? Getting through this one?
Professor, may I ask a quick question about how you did that last section?
Yeah, absolutely.
So, even though the answer would come out less than 7/4 to the end, like we wanted to, we just kind of found the nearest one so we could cancel it out and get 7/4 to the end.
Exactly. That was our whole
Okay.
goal. Try to
Okay.
find a way to force that in and critically maintain that right direction there in the inequality.
Huh. Okay, cool. Thank you.
Yep, absolutely. Any other questions so far? Okay, let's imagine this is a real final exam question. It's worth 10 points. I'm thinking this is going to be pretty challenging, but you could make some pretty good partial credit work in this direction right here, just by starting it off here and trying something. A lot of people might find some moments of inspiration, maybe flipping back to the problem and just finalizing it. But even if you did complete it, you might lose a few points. But I do intend to curve the exam. This problem is on the exam. The exam's probably being curved by at least 5 points at minimum, because I know it is a challenging problem. But let's try out a more routine problem next. We're now in chapter 7. The whole purpose of our chapter 7 in this book was to think a little bit more about pseudocode algorithms, tracing algorithms, and we used really just number theory as our main vehicle of examples for that kind of work. First problem right here says, find unique integers d and r such that n equals kd plus r is between 0 and k. But all this really is just the division theorem. This was a real exam problem that we're taking, and you can probably imagine that it probably is going to be one, either with n positive or negative. The thought is, just as a reminder, this document is going to be, hang on, let me take a look here. I think I forgot to post my notes here. I do intend to post the actual problem, or the actual formulas are going to be there on the final exam. Somehow I must have missed that. Let me put in a really fast reminder. Post the last page on the final exam, which is going to contain a formula sheet for us. Sorry, I somehow must have forgot that before I came to class today. But different formula sheet could be, say, this one right here. You'll have a formula sheet just like this one. And what we want is this one, the division theorem. So if you're doing this problem on a final exam, it's a good idea to just take a look at that division theorem. Here it is. Let's pretend this screenshot is us looking at the division theorem, flipping back to the last page of the exam. And now we just need to run through this, what's usually called the division algorithm. First thing we do is just do the modulus part. We are going to take n mod k. In this problem, it's going to be 23 mod 6. And people are pretty fast at modular arithmetic, I've discovered in this class. But this is one where it's kind of valuable to just take your time with it. Let's use the actual formula for this one and write this in as 23 minus 6 times the floor of 23/6, because this gives us two things we really need. We're going after d, and we're going after r. The value of the modulus arithmetic, or the modulus here, is r. But now we have this value as well. Let me just run through the formula. So this is 23 minus 6 times the floor of 23/6. Let's run through that real fast. The floor of that is just going to be a 3. So 3 goes into this position, and this is identified that d equals 3 in the division theorem. Then this is now equal to 5. A lot of people would look at this and just say 5, right, just by visual inspection. But that's now giving us the value for r. R is 5 through this value here, the result of the 23 mod 6. At this point, we're done. We found the integers d and r that satisfies n equals kd plus r. This problem is one of those faster concept kind of questions where it really does pay a lot to do the extra check. It's not required, but let's put it in. If these are the right values in the division theorem, then we'll have n equals kd plus r, with this big requirement that r is bounded between 0 and less than k. Our n value is 23, equals the k value of 6. We found d is 3. plus r is 5. That's 18 plus 5 for 23. So it does balance on the equation. So that means this one is complete right at that step. Kind of a relaxing problem after the last one. Any questions with this one so far? Okay, so that's the good old division theorem. Other things we could be doing in the final exam is some properties of modulus or modular arithmetic. These ones we made a pretty big deal out when we computed them the very first time. They showed up on the exam. Everyone did a really good job of this, showing the steps directly using the properties. Let's do that again, but this time I want to show you what it would probably look like if you've been doing this for years and years, and you just want to write it down, really showing the steps, but not making a big deal out of it. The first step in this property right here is you take the mod 10 of 112. Well, that would just be 2. You take 95 mod 10. That would just be 5. Then you take that whole result, mod 10. But that's just 7 mod 10 for 7. Our work is done right immediately at that step. So if you did it that way on the final exam, I would say that's excellent. That's a good indication to me that you've done these properties a lot. You know exactly how they go, and you're not going to make a mountain out of it. This is just the essence of those properties. Does that look all right to folks on that part A?
Absolutely.
Awesome. Kind of a slick trick as well, because I mean, without that, if I wasn't thinking of properties of modular arithmetic, I'd be looking for my calculator. But these properties say, if the problem is rigged just right, of course, you can just kind of eyeball it and get a number out really, really fast. Let's try it out again. In this case, we're going to take 56 mod 5, but that's just a 1. 43 mod 5 is just an 8. Excuse me, a 3, because 5 by 8, I think my brain was trying to say, is 40. Mod 5. We're done. 3 mod 5 is just 3. So kind of fun and satisfying in a way, because that looks like it could have been a hard problem. But the closer you look at it, it's really just that. Any questions, folks, on the part B? Okay, let's try it out one more time. Really, part C is no different than part B, because part B is a multiplication property, and this is just repeated multiplication if it's 7 power 4. But same exact thought applies. Take the base mod 4 first, that's just 3. Now raised to power 4, mod 4. A little bit more steps on this one, really, but 3 to the power 4 is 81. And, well, 4 goes into 80 evenly, so 81 mod 4, automatically a 1. So these problems could take a while if we were doing on the third exam, but you might notice it really just boils down to that. That's a fair way to do it on the final exam as well. These problems can sometimes go pretty fast. Sometimes they take a little bit extra analysis to get through. But any last questions, folks, on the modular arithmetic portion? Okay, let's try out next. Another really fast concept question. This is still in section 7.2. It's asking us how many primes approximately are less than or equal to a pretty high order of magnitude on 10. But we have a really great estimate on that one. We did some trickier problems too, like how many 8-digit prime numbers are there, stuff along those lines. For this kind of problem, all we need to write out is, if you're using the author's notation, you might say primes n is approximately equal to n divided by the natural logarithm of n. The n value for this is just 10 power 19. Then we divide by the natural log of 10 power 19. You can use some properties of logarithms in here just in case it might help, but 10 power 19, 19 times natural log 10 is not a huge improvement of what we see on the left-hand side. And over here, just throw that into a calculator. This is going to be some order of magnitude. we'll have 10 power 19, divide by 19, natural log 10. And so I'll just report an answer of this is about 2.285, 10 to the power 17. Order of magnitude seems right from that divisor. So 2.285. 10 to the power 17 primes. And we did say approximately in a couple steps here, so we're being honest, we don't know exactly how many. We can do some really hard computations to figure that out, but this is what we're expecting. And we're expecting it to be pretty accurate because this estimate improves as n gets larger and larger. So here we were just counting primes less than or equal to 19. Any questions at all, folks, with that kind of strange looking computation? Okay, on to the next one then. Here's where it gets kind of exciting. Tracing an algorithm. Again, that's kind of some of the purpose of what our goal was in chapter 17, working with pseudocode. So pseudocode will be provided for this kind of problem. See if we can get a good zoom on this. And we did do a trace of things along the lines of mod and div. We did a trace of the Euclidean algorithm, and on homework, we did trace the extended Euclidean algorithm. But let's say for the sake of just making this problem a little bit more fun, I have some interesting values here. Let's change this one to 52. And that's going to cause a little bit more recursion to happen in this kind of problem. Let's give some practice in that direction and see how it goes. Just as extra advice on the real final exam, I do intend to post a problem just like this one, where it's going to have some extra recursion to go in. We practice doing it with not very much recursion, only one called to the else right here. This one's going to have multiple else block executions, so multiple recursions. There'll be a final exam question where most of the credit is just getting through the first part. Again, if you make any good progress toward the second part, the multiple function calls over here, you're getting a lot of credit in the problem, and I do curve the exam since it is a challenging problem. But let's give this a try. We're change the problem to have a more interesting situation occur on this one. First, we can say on step one, we're going to call extended, I'll abbreviate to just ext, Euclidean algorithm at 1852. Let me rearrange the screenshot since we'll have multiple reasons to take and double check that as we go. First thing we have to look into this algorithm is what should happen. We have the right input, n and m, with m being bigger. Doesn't hurt to say that though. Here's the n, and here's the m as inputs. When we call this, the output is defined to be xyz, xyr and z. So we could say xyr, this is going to be our final return, is defined to be extended Euclidean 1852. So next thing we do is we see if this block is going to execute, n mod n. So n mod n on this function call is going to be 52 mod 18. And we had all those fancy little properties of modular arithmetic, but this problem is not rigged so nicely. Some people are really fast at this, so if you've already got it, that's great. But just for the sake of getting also the floor at the same time, let me call mod and div 52 mod 18. So 52 mod 18 is 16, and the floor of 52/18 is 2. So let's recall those values, 16 and 2. 16 goes here. We're going to need this result later. Floor of 52/18 is 2. And now we make a check. This is not 0. And so that tells us the else block is going to run. I'll just say here, go to else block. So now we're on step 2. In the else block, we make a recursive function call to extended Euclidean again, but now with new inputs. And let me finalize that not equals 2. That's kind of jarring not having a number there. Any other questions, folks, on step 1? Okay. I think one thing that happened on the homework that was really kind of cool in a way is when people did this kind of problem, they did a really in-depth trace. Not everybody, but there's a couple people that did a pretty in-depth trace of using the other helpful functions as well as going through this one. But I'm going to have the screenshot a little bit better targeted on the real exam to just say, I'll screenshot this part right here so that this part is not a distraction, making us do more work than it's really intended. So on the next step, we're going to call this part. And let me say just briefly, I can't say XYR any longer because that already has a meaning. So let's go X1, Y1, R1, define to be the function call of extended Euclidean. Well, the result of the function call is probably a better way to say that. It says first take the value of the mod, which was 16. Take the value of n, following this line right here. N is the right-hand part. So 16, 18. And, well, we're really just rerunning step 1 with a whole new function call, this Euclidean right here. So let's just, with strong parallelism, take the same exact steps. Do n mod n, which is now 18, mod 16. That one's a little bit faster. 18 mod 16 is just definitely a 2. We also want to know the floor of 18 sixteenths. Floor of this is just going to be a 1. And next thing we do is, this is a whole new function call. So we're starting over from the very top and looking into this part. The modulus is not 0, so this tells us go to else block. So we're back down here. That is going to be our next third step in the trace. Let me know if any of this goes a little bit awry. Again, I'm working on a little bit of insomnia, but we're going to definitely get through this one. Does it look all right to folks at the moment? Okay, so far so good. Let's reuse this strategy. If we're going to call or go to the else block, we're going to call extend Euclidean again. So let's call this x2, y2, r2 is going to be defined to be the return from the call of extended Euclidean of, let's take a look. We need the value from the mod. That was 2 right here. Then we need the n value. N from this structure informs us it's got to be 16. That's starting to look like it's going to eventually end on us. So the extended Euclidean at 216 brings us right back to the very top. We now do a n mod n check. This time it's 16 mod 2. And this time it is 0. It's a moment of celebration because that means we're done with all this recursion. This time we go to the if block. So we have a return. It's not going to be our final return, but we get to return values 10n to Euclid 216. That's going to provide values for x2, y2, r2. And then we just go backwards until we get to the original function call, Euclid 1852. So let's maybe make this our step 4. Now in the if block, this is exciting. We're actually returning values, not calling a function again. So let's say here, return 1, 0, n, which is going to be 1, 0. One thing that makes this kind of foggy is, what is n? It is not 18 any longer because that's the original function call. We have to think, how did we get to the if block? We got to the if block from that function call, Euclid 216. That's the n n value, or we could just look at m mod n again, tells us it's a 2 in this position. So we're returning 102 to extended Euclid 2/16, which means we have values for x2, y2, r2. Let's list them out. In order, it's the returned values right here. I'll just say this implies with the right arrow, x2 is 1, y2 0, r2 is set to 2. So we've got values returned to us. Now we can wind backwards and give these values back to extended Euclidean 1618. Any questions first on this part right here? Or really any part? Okay, so on to step 5 next, depending on how you decide to order them. We have values being returned. We are completely done with the execution of Euclid 2/16. And now we're in Euclid 1618. Oh, that's not a good level of zoom. 1618. When we're in this position right here, trying to get to about that level of zoom, we are right here doing this return. So we're on Euclid, just temporary marks, 1618, returning these values. And when they get returned, they define finally x1, y1, r1 through these values right here, which are referred to as just a y, x, xr. So let me zoom back in so we can see that a little bit more clearly. We'll say here, return these values to extended Euclid 1618, just double checking those numbers. Here, this one has a return, and we're going to write it out in this format. It tells us the first part right before that comma is x1. x1 is going to be defined to be y2 minus the floor of m and n, but we're on this function call. So it's going to be the floor of 18/16 multiplied by x1, x2. So now we can calculate x1 through that formula, and we're finally feeding back the values on that return call from Euclid 1618. So on this line, we have y2 is 0 minus the floor of 18/16 we compute as a 1, and x2 was a 1 as well. So x1 is now defined as a -1. The next part is a little bit nicer. It says the second element returned, which is referring to y1, is just defined as a x1. Let me wind that back, defined as x2. The subscripts here looks like the trickier thing. x2 is defined as 1. So we have our y1 value. And there's nothing tricky about the final return. R1 right here is directly R2. And these values are going to stay the same all the way back to the top of the original call. This is the greatest common divisor now. But let's just track it through. Our job is to trace it. So there it is traced. So we're done with Euclid 1618. Now we go to Euclid 1852. That looks weird written in at that step. Let's just call that a step 6. Before we do that last step 6, the final return to the original function call, any questions at all, folks, getting these values? Okay, so now back to step 6. We took these values from Euclid 2/16, used the formula on the very bottom for how that return should go, gave it back to Euclid 1618. So now we have an x1, y1, r1, but these values go all the way back to Euclid 1852, where XYR was defined to be, let me write that in a slightly better notation, the output to that function call. So now let's say back to Euclid, and keep forgetting those values, 1852. We said the floor of 52/18 is 2 on that one, so we'll use that value as well. This function call has us right here. We did the recursion, and the next line is to return this information. The final return is going to be x. Through the formula, it's going to be y1 minus the floor of 52/18, we compute as 2, times x1, so let's throw in those values. 1 to start, minus 2 for the floor, times x1, -1 value here, gives us x has to be 3 on this return. Next value y is going to be the x1 value, and x1 defined to be 1. Last thing r is directly r1, which is 2. So never any changes when we get to the bottom of the recursion, work our way back up. R is always going to stay that fixed value. So this is the final return. That means our job is totally done on the trace. But the trace is kind of foggy sometimes when we're dealing with recursion to tell if we really have the right values. So here's our bigger check. We really have the right values. This output has to satisfy this condition. We had n is 18, m is 52, and let's take a look into the function values. R is the greatest common divisor, which is 2. So let's see if 2 is really equal to x, a return value, which is 3, times n, an input, which is 18, then plus y, a returned value, this one is a 1, times n, an input, which was 52. So if this equation hands out as correct, that doesn't look too good, does it? Something must be awry with this. So we've got a bug in our trace somewhere. Anyone happen to see where it could be?
I'm not sure yet.
Oh, I think I spotted it. Our x1 was -1, and I just dropped the sign right there. That's a bad spot to drop a negative sign, but throw a -1 inside there. And we've got, let's see here, the y value that goes in that position was really negative. This looks plausible. Let's grab the calculator and see if we can track that change a little bit better. Let me put a little box here to say that's where the error was. Potentially, let's see how close it gets. So the right-hand side is 3/18 minus 52. Yeah, it came out as the greatest common divisor 2. So that tells us our trace actually looks like it was successful. Well, how do folks feel about that one? Does that make sense on doing this kind of trace?
I just want to make sure I'm understanding, Professor. So every time you run through extended Euclid and you get a
Yeah,
return, you're keeping track of those values to pass back to the previous one you went through.
exactly. And
Okay,
when you do it in this kind of way right here, where you have
right.
to keep rearranging those values through the formulas, unless you get to the very bottom where the if executed, that's happening right here. In that case, you just define x, y, r as exactly those values in order. But then you grab those values, feed them back to the function calls moving up a level each time, using that information every single time.
Gotcha. Okay.
Well, we did this as a homework problem where it was only one recursive function call. That made it a little bit more trackable for homework. On the exam, if you can get to that one recursive function call, on a 10-point problem, I would probably give a lot of partial credit, maybe 6 or 7 points. Any progress you make going forward, and in turn, feeding the values back in this way is going to give you the rest of the credit. But any last questions at all, folks, on this one? Okay, well, we've got about 5 more minutes to spare. Problem 18 is a full multiplication table for Z8. We did this one in the homework, I think, for either Z6, maybe Z7. I think this one's going to take a little bit more than 5 minutes. How about for the last problem of the day, let's try out Fermat's theorem. I'll come back here on the notes and upload the solution to this one as well. And I did put in a reminder, thought I had this placed already. On the final exam, I need to put in the probably right around here, the actual formula sheet that's going to be provided on the real final. Sorry for taking some time to put that on there. But let's make this our last question of the day, or last problem to get through the day. Verifying Fermat's theorem for P5 and A4 is really just a statement that for A in ZP for P prime satisfies A to power P minus 1 is equivalent mod P to 1. So just a really fast concept question on this one, last problem. If A is 4 and P is 5, we're going to take a look into 4 to the power 5 minus 1. Now let's do that mod P, since we're looking to congruence mod P. P is 5 here, so this is our computation. That minus 1 kind of messes up our modular arithmetic. Well, let me think about that. Not necessarily. This is 4 power 5 mod 1, so this becomes, excuse me, mod 4 to power 4 mod 5. Now if we think in terms of our properties of modular arithmetic, well, 4 mod 5 is 4. That's not too helpful for us, so 4 power 4 mod 5 still looks like kind of an interesting problem. So let's throw this into the calculator. 4 power 4 is 256. And that's helpful. It's 1 off from 255, of which 5 does divide evenly. So this becomes 256 mod 5, which is exactly the one that we were trying to get to. So that's our Fermat's little theorem. This one will be just a really fast concept question. The formula for this one would be provided. We didn't do a lot with this in section 7.4, but its major role was how it works with cryptography in section 7.5. But we got through just about all the problems. On the last one, Z8, we would write out a set, 0, 1 through 7, and just do the multiplication table through more modular arithmetic like this, but not with crazy powers on the left-hand side. But any last questions at all, folks, before we call it a day?
Professor, will we see anything from 7.5 on the final besides the Fermats?
Oh, so for 7.5, it won't be Fermats, but it's going to be either, let me go back to this one. I'm going to give an extra credit question based off one of these two problems.
Oh, okay.
It's going to be this problem right here. Probably a more appropriate problem since this is a little bit more easy to compute on a paper exam. If I try to go through this problem, I'm going to have to only give certain elements of it since certain parts of this are really kind of hard to compute.
Yeah,
So
okay.
either one of these are going to be an extra credit question. All the questions about that so far? Okay, kind of the spirit of the extra credit question 7.5 is when you take a final exam, oftentimes, your mind can go blank on a concept you really know. So I'm going to give the extra credit to one of those questions to be substantial enough. It's like a problem swap. There's a problem on the final exam that maybe it's not your favorite problem, or maybe you just went blank on that one. Go to the extra credit question, compute that one instead, and it's not going to harm your grade. That one can be like a full problem swap. And if you solve all questions on the exam, including the extra credit question, that's even better. But your exam grade can't exceed 100%. So in that way, the extra credit is more of a problem swap in spirit. Well, I think I've ran out of things to say. My goal is before probably early morning on Thursday, include those notes so you have a good idea what problems are really going to be on the final exam. I'm going to next, probably on Friday in the morning, start scanning your exam threes, get them returned back to you to help with some studying. And aside from that, if any questions come up while you're studying for the exam, don't hesitate to email. Going from close week into finals week, I try to be very available on the email. But have a great night, folks. I'll see you all later on.
Thank you.
Yep, take care.
By the way, Professor, how did your wife's procedure go? Did it go well?
It went pretty well. The precision went through the muscle, so he's got some recovery to get through on that. And they did a nerve block on that arm, so we learned a lot of anatomy. A nerve
Okay.
block means a shot right here in your neck that goes right above your lung, and it just wipes out your whole arm. So he's kind of have like a marionette arm for a little while. But we're expecting a good procedure on that. They didn't have to actually move the nerve over or anything like that.
Good. Wonderful.